Getting the best from Chemistry Explained needs you to participate. So write notes, complete tasks on paper or tablet. Pause and control the pace at which the lesson goes. Crucially, complete the tasks when prompted. That means pausing the lesson, taking your time, thinking the problem through. Only when you're ready, continue. Correct your work before moving on to the next slide. Heterolytic electrophilic addition. So we need to know what an electrophile is. It is an electron pair acceptor, usually a positively polarized or possibly charged atom. So let's look at an example which we will meet later on. Bromine delta plus, a positively polarized bromine atom. Now, it's got to accept a pair of electrons. Well, that process is indicated by a curly arrow. So that curly arrow means a pair of electrons is moving in towards or onto or close to that positively polarized bromine atom. That process results in the formation of a covalent bond. So we've defined electrophile or electrophilic. What about heterolytic? Well, fission, let's start with that, refers to the breaking of a covalent bond, and we've met homolytic fission in the chemistry of the alkanes. But here, one atom of the bond, of the covalent bond that is broken, receives both the bond pair electrons. If you recall, on homolytic fission, the electrons are shared one each between the two atoms of the covalent bond. So there's two atoms, A and B. There's a covalent bond. Could you draw in the appropriate curly arrow if A is more electronegative than B? Pause and resume when you're ready. Okay, so if A is more electronegative than B, then the heterolytic fission would tend to have A receiving the bond pair and B losing its share of that pair of electrons. So could you predict the two particles that are formed? So pause, write down your best prediction for the two particles that are formed with all the necessary detail. Resume when you're ready. So if we look at the two possible particles, we'll see that the bond pair that was here is now positioned as a lone pair on the atom A. And A has picked up 2 electrons, so it has become negatively charged. It did have a share of the bond pair, so now it has sole possession of the lone pair, so it is 1 negative. B, on the other hand, used to have a share of the bond pair. It's now lost that share of the bond pair, so it is now positive. So heterolytic fission usually results in the formation of 2 oppositely charged ions. So I now need to discuss the electrophilic addition mechanism for the reactions of the alkenes. So let's take an example, hydrogen bromide. Hopefully you're familiar with that, hydrogen bromide plus an alkene, an addition reaction. So let's draw the structure for any alkene, and then let's bring in a hydrogen bromide. Now hydrogen bromide, of course, has a polarity. Bromine is more electronegative than hydrogen. So the electrons from the hydrogen bromine bond will tend towards the bromine. Now that means that the hydrogen here is delta plus and acts as an electrophile, an electron pair acceptor. So we need to draw in some electron pair movements. So the electrons from the pi bond of the carbon-carbon double bond move out towards the electrophile, the hydrogen delta plus, and that electron movement repels the electrons in the hydrogen bromine bond onto the bromine atom itself. So could you now draw the structures that result from that those two electron pair movements? Pause the video and resume when you're ready. Okay, so here is the first structure, a carbocation. We've got the electron pair that was in the covalent, the pi bond is now here forming the bond pair between the carbon and the hydrogen. So that means this carbon here has lost its share of the pi bond electrons, so it is now positively charged. But what other particle needs to form? Well, we need a bromine particle, and that now has a lone pair of electrons. It did have a share of the bond pair. It now has a lone pair of electrons, and hence it's in effect acquired an electron, so it is negatively charged. That lone pair of electrons moves on to the carbocation to form a carbon-bromine bond. Could you draw the structure of the product? Pause the video and resume when you are ready. So there is the resulting fully reacted molecule. So we've got addition of HBr across the carbon-carbon double bond. A little bit of vocab. Hydrogen bromide is the electrophile, and I did mention that the carbon structure there is called a carbocation, positively charged carbon structure. So we now need to discuss the addition of bromine to the carbon-carbon double bond. Now the starting point is slightly different from the hydrogen bromide reaction in that the bromine-bromine molecule, Br2, is non-polar. So we need an initial step whereby the bromine molecule approaches the electrons of the double bond and the electrons in the bromine-bromine bond are repelled, so that we now form a situation where we have bromine delta plus and bromine delta minus. That is, the electrons in this bond have been pushed towards or away from the carbon-carbon double bond onto the bromine delta minus. From that situation, we believe the mechanism follows exactly the same pattern as for hydrogen bromide. Could you complete that reaction, please, with all the necessary steps? Pause the video, come back when you are ready. Okay, so we need to insert some curly arrows. So the curly arrows come, notice, from where the electrons are and to where they finish. So it's very important to start the curly arrow precisely where the electrons are to start with. Those electron pair movements result in a carbocation and the formation of a bromide ion. The bromide ion has a lone pair which will attack or be attracted to the carbon bearing the positive charge in the carbocation. Please note that the curly arrow begins exactly at the lone pair of electrons and ends up approximately where the carbon-bromine bond will be formed. So our next step would be the final product, the dibromoalkane. So we can use the ideas of heterolytic electrophilic addition to explain Markonikoffs' rule. Now, I'll just remind you that Markonikoffs' rule refers to the addition of a molecule such as hydrogen bromide, which is of the form HX, adding across a carbon-carbon double bond within an unsymmetrical alkene. And the rule simply states that the hydrogen will add to the carbon that already has the more hydrogens. So we would expect to see the carbon on the left-hand side gaining the hydrogen. That means the bromine should add to the carbon here of the double bond on the right-hand side. And the major product will be the 2-bromo compound. Now, the explanation lies in the stability of the carbocation intermediate. So to form the major product, the carbocation would form with the charge being carried on the central carbon. That is a secondary carbocation, by which we mean that the charge carrying carbon is bonded to two alkyl groups. The bromide ion would come in here and form the 2-bromo product. If we look at the carbocation that would lead to the minor product, we see that the charge-bearing carbon is on the end of the chain and is part of a primary carbocation. That is, the charge-bearing carbon is bonded to one alkyl group. That would lead with the bromine coming in here to add to the charge-bearing carbon to the 1-bromo alkane product. That's the minor product. Now, quite simply stated within the OCR specification, simply need to realize that the secondary carbocation is more stable than the primary carbocation, which means that the major product is much more likely to form and the minor product is much less likely to form. So you need to know the relative stability of the carbocations and apply that to explaining Markonikoffs' rule. So the simple relationship is that a tertiary carbocation is more stable than a secondary, is more stable than a primary. And it's the stability of that intermediate that determines the major and minor products. So what I'd like you to do is to draw a structure for a primary carbocation, a structure for a secondary carbocation, and a structure for a tertiary carbocation. Pause the video, draw those structures, resume when you are ready to check your answers. Okay, so I'm going to reveal a primary carbocation, and you can see here that the charge-bearing carbon is bonded to one alkyl group. A secondary carbocation, the charge-bearing carbon is bonded to two alkyl groups, and the tertiary carbocation, the charge-bearing carbon is bonded to three alkyl groups. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers, move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.